Just kind of did an all-nighter, and I think I'll just try and solve some LeetCode problems to improve my tree, specifically tree problems for as long as I want to do it. So here we go. 111 minimum depth of binary tree. So we're given a binary tree, we have to find its minimum depth. So the minimum depth is the number of nodes along the shortest path. Root node down to the nearest leaf node. So leaf node is a node with no children. So here we have an example. We have this tree over here with the root of 3, and then we have a bunch of these children. And we want to output 2 because there's 2 nodes in the shortest path, which is 3 to 9. Okay, so I guess this is like it's kind of like a top-down approach where from each node we calculate the shortest path, and then kind of just like push it up to the root, and we want to ensure that, like, for example, at 20 we want to look at like its children. We see that there's 15 and 7. The shortest is 2 because both they're same depth, and then we bring that up, and at 3 we now know that the depth here is 3, but here it's 2, so we just have to return 2, which is smaller than 3. So since we have to kind of travel all the way down to the all the way up to the root from the children, I think we'll use a depth first search. So I'll find a DFS inside of the main function. So this will take in a node, and it has to return an int. And then we're going to call that DFS with the root and return that actually. So what's the base case? So base case is obviously we stop when we reach a node that is none, or when there's no more node. So if not node, we return. And what do we return here? Is we return 0, because say we traveled all the way down to the right, we see that there's no node, we return 0, 1, 2. What we should actually return 1 here. Yeah, because we're not counting the what's it called, the branch, but we're counting the number of nodes. So if we know that the current node, like, it doesn't have anything, we at least know it has the parent. So we'll return 1, and we'll do left equals right equals DFS node dot right. So this will just travel all the way down to the left and return 1. We can't stop there and we have to add to it. Oh, but I guess if we're doing it like this, we can just do 0. So yeah, we enter this function with a node. Doesn't meet the condition, go down left. Inside the left, we go down again. We got 0 plus 1. Plus 1 again. Now we know it's 2, the path. And then we go right. We invoke the function, we go left. Okay, so we want to return minimum of left and right. So what happens here? So first we go down left. We go down to the child. We look at its children. They're both none. So we return 0. So here we have 1. Then here we have 2. And now we want to go down right. So we call right. And then we go left. And then left. So 0 is returned here. We add 1. And then we go right. 0 is returned here. We add 0 or 1. We get the minimum, which is 1. And then that's bumped up again. Plus 1 from the left that we called previously. So here now our left is 2. And if we call right, we'll kind of get the same number here. So we get 2. Minimum of 2 and 2 is 2. And then we add that up again. And then finally, we do the final comparison between the left subtree here and then the right subtree here. And then we get the minimum value. So I think this is a solid implementation. Let's test it out. And it's wrong. Okay, let's take a look at the second example. So it's 2 left, we don't have anything. 3. Oh, so I think here the problem is we're actually counting the node itself. And I don't think we want to do that here. Let's look at the current node here. Let's see if it's... Oh. Three, 4, 5, 6. So we went all the way down there, but 2. 2, 3, 4, 5, 6. I guess this was wrong. Get the minimum of left and right. So the tree kind of looks like this too. And then, so if we kind of like collapse it to the left, it should look like 3. And then here there's nothing. And then 3 has let's see. 3 has nothing, and this is kind of confusing to see. So 2 null, 3 null, 4. So I'm guessing that's like the left child of 2 null, 3 null, 4. Yeah, and then null, and then like 5, and then like 6. Is this kind of like what's going on? But the problem with our approach is that so we discover left here, came up, that's a 1 on the left stored right here, and it will just automatically return 1 because although there's nothing on the left, because so I think one way we can do is we can just do this. Might not be the best answer. And then we can do like min here again, I think. And then +1 because we know the node is there. Oh my god, this is so stupid. What? Left. This should have returned like 0. Oh, so, but okay. So it returned 1 anyways, cause but we literally just put in none. What? It should put in an error here. This is none, literally. Oh my god, I keep doing the same mistake. God, I fucking suck at trees. Yeah, exactly, this is a none, so this should have just returned a 0 here. Oh, but it got the... Okay. So one way I think we can do like, if left is 0, we return right +1. And then else we can just do like min. Yeah, this is one way. I'm pretty sure this should work. And it returned a fucking, like, what? Okay, let's look at the... Some tips. Let's go look at what this guy said. If root is null, return 0. I did that. Otherwise, keep in mind that roots depth start at 1, not 0. only check min depth for left nodes, meaning a node who has two null children. Updating min on every single node when they should only be updated for leaf nodes. Okay. Doing it recursively, you can save content by adding updating min every single node. That's essentially what I'm doing here though. Updating min on symbol. We shouldn't do it on every single node, but we want to do it at the leaf node. Okay. Let's kind of think about what that means. So left went down all the way to the left side. Minimum depth. I know I solved this at one point, but I can't remember the solution. We have to return max. This looks so out of place. Yeah. Okay, let's just try the BFS implementation. I feel like that's just way much simpler. So we have a queue with our root in it, and so that 0. So while there is an element in the queue, plus equals 1, so current node is dot left. Oh wait, we have to capture the size too, because so for stuff and length, we want to just put everything in there. Okay, let's try this approach. Maybe I just do it like this. Oh, it's append, I guess. Add is for set. Wait, now it's working for case 2, but not for case 1. That's hilarious. Okay, so yeah, so we plus 1 the depth because we're dealing with node here, like the root here. So, and then okay, so only add depth like if there's left and right. Okay. Yeah, we can just move it here, I think. Yeah. Current equals pop q dot pop left. Okay, it has been 25 minutes, so I think I'll look at the solution. Try my best to understand it. BFS, DFS. Okay. Each subtree and compares the depth. He says it's a more natural fit, sure. Initializes a queue, depth 1. Queue is not empty. What? Okay, that's a terrible solution. I'm looking for something more descriptive. Very easy, 100%. And just pastes a fucking wall of code here. But I'll try to read it. Okay. If they're both empty, sure. I think I should just watch LeetCode Solution. Minimum depth of binary tree. Okay. I guess he hasn't posted about the solution.
Let's just make sure we haven't made any syntax errors. Cool. And let's submit this. And it works. Cool. And in this case, we actually need to check whether or not our current depth is actually smaller than our minimum depth. So we're going to say if not, node.left and not node.right, because remember, a leaf is a node with no children. So if it doesn't have a left and a right child, therefore it is a leaf. What we want to do is we want to say
no, I think like I don't really like his style of code. Like I'd rather just not do like global variables. So try to look for like other solutions, or even better, just ask Gemini, where I have all my LeetCode stuff. What is an optimal solution? What? Oh, this is another question. Okay, never mind. What is an optimal solution? Spot on, okay. Minimum that BFS is actually more optimal than DFS because the wet level. Okay, so moment you see a leaf, you just return immediately, I guess. Is that what it's saying? Let's see. Okay, it's getting closer. Missing by 1 for some reason. So here we got the brute, put in 920 and popped those two. Okay. Handle the base case here. What do we got afterwards? Okay. Okay, I guess this is much simpler than mine, so sure. So first stuff in current queue. That's kind of what I did. Okay, cur equals q dot pop left. If not cur left and not cur dot right, return depth. Otherwise, oh, okay, so the difference is that we increment when we're done with the what is it, the level. Okay, so if cur dot left, we append it to the queue. Right. So here, when we're done with one layer, we plus one it. So here, like first layer, we're done, we plus one. Depth is now 1. Second layer, we're done, plus 1. Okay, so we put left in first. So left came out. Doesn't have any children. Sure, you just return the depth. So we looped over everything in that layer specifically. And if it doesn't have any children, which means it's a leaf, we just want to return the current depth right away. That's kind of confusing because, like, what if you look at the longer path first? Like, what if the thing you popped was like 20 instead of 9? Oh, but then that's fine because we're incrementing depth at the end of the current layer. So inside of this loop, the depth doesn't change at all. Okay, and then if we find the leaf here, we know that it's the shortest path anyways. Or the minimum depth. Okay. But if we had to use DFS, it says, careful about the skewed tree trap. You can't just do this, which is what I did, because if one child is none, that's not a leaf. Just an incomplete path. Okay. Let's look at this code as well. So base case, sure. If one child is none, we must traverse the other paths. So if we don't have left, we return, okay, self.min depth. So we go all the way down to the right end, check left, right, it's a 1. So we return the minimum of those two, and then we just kind of go up, I guess. Okay. Good. Cool. I think that was a pretty solid one question I can solve before I start my day. Kind of embarrassed that I couldn't solve this. Although it's an easy question, because it's just not good at trees. Come up with the next video. Hopefully I can do better. And just trying to get better at these 3 questions. Okay, see ya.